Okay, here we are, chapter 2, EO 164 online version. It is here in chapter 2 we're going to be talking about PLC hardware components. Starting out with section 2.1, I/O section. So again, we're going to talk about some more I/O, input and output devices, which I/O means. We again are going to compare a few different components here. Looking here on the left, we see the fixed I/O PLC, or often called brick, or fixed PLC. Then up right, we'll see a modular PLC where we see a power supply, a CPU, and a series of input and output modules, making it modular. So input interface modules accept signals from machine. So essentially what they're saying here is that you can have a series of inputs and output modules. They're going to be receiving signals from the equipment, and the output module will be transmitting information to outputs, turning lights on, turning motors on, turning valves on, that sort of thing. Communication modules. Now, I mentioned that before. A lot of the new PLCs have a communication module that slides into them. Many of them have a communication module attached to the processor already. So they're able to communicate to other remote I/O, remote locations. In this particular example, they're actually showing an expansion rack, where an expansion rack is connected to the main rack, allowing it to have remote I/O. In the old SLC 500, I'm going to briefly review this, but it's just essentially what they're looking at here is the addressing of it. So the address is based off several components. First of all, what slot the input card is in. So when I'm looking at a multiple racked PLC, whatever slot that input is in, that is going to be determined by this guy here, the 2 here. And then the number down here is going to be the terminal number in that slot. So here we are looking at the 500 format again, looking at some different addressing. So module type, input or output, it would be an I or an O, depending on whether input or output. File number, this is just something that Allen Bradley uses. It's not, you don't have to show that in the program. They're just making you aware that input is 1, output is 0. Element number or slot number, that's the slot, the location in the rack. And then the bit number, which wire or which terminal you landed the input to on the rack, on that card. Here they're showing how the address ties to a location in the PLC program. So if I tie this to terminal 1, this happens to be slot 1, so I get input 1/0 being the input 1, slot 1, input 0, slot 1. So when that state does turn on, as you can see, it turns to a 1, and it highlights that contact as being closed. This guy here is an open state, which is slot 1, bit 1. That's in an off, so it means it's open, so it's off here, so you will see this not highlighted. Because that's not highlighted, this is not highlighted, that output is off. And analog I/O modules use a whole word of information. We're going to be getting into this further down in when we get into later chapters. So I'm going to just briefly describe how this works. Essentially, everything we've discussed up to this point has been either an on or off state. This is talking analog, where I can have any value from, say, 0 to 10, or 4 to 20 milliamps, depending on the application. But it gives you an idea that I'm not looking for just a straight on, off. I'm looking at any variation in between, anything between 0 and 10 volts. So it gives you a little more flexibility helps you define like how full the tank is and that kind of thing. So it gives you more control, whereas you either have the tank empty or full with on off. But here you could say that the tank is got 1 gallon in it versus 10 gallons or 3 gallons or 4 gallons or 5 gallons. As it's filling, you could see every gallon as it's filling into the tank, kind of like your gas gauge on your car. You know, if you had just on off, it would be you either had gas or no gas, and that would be digital. If you're having analog, you can watch your gas gauge go down as you're getting lower and lower on fuel. So you get a pretty good idea when you need to add fuel to it. Again, we're talking the Allen Bradley I/O addressing, the older format of it, so I'm not going to get into too much depth here. Just going to make you aware this is how it is laid out. The local 6.1 data 0, this is the new format we'll be following, but as we get further and further into the 5000 software, RSLogix 5000, we will be getting learning more and more details. This is a PC-based card. We're not really going to get too involved with that. Again, talking some more inputs and output modules here. Status lights. This is some good information. So you'll have each one of your input cards will typically have a status light. Those when you close the contact to one of these terminals, you'll see the light come on in front. What that does is give you the immediate acknowledgement that yes, the input is coming on, without having to open up the PLC or the laptop, excuse me, to figure out if that input's coming on or not. If you can see that signal come on in the light, then you know at least that input is working properly. They're just stating here that in the event you had to replace a PLC module, most of your PLCs have a replacement terminal strip, so you pop this right off. You're able to pull that card out of the rack, put a new card in, and then return this terminal strip right back to the card without having to unwire a single wire. Just it's a maintenance thing for when cards fail and you have to reduce and repair. Here's some different versions of input cards. You got 8, 16, 32, or 64. You'll see a lot of variation in that. A lot of your cards that we deal with on a regular basis are at 16. I think you're going to see more and more in the future where people are going to more than 32 and 64. In the higher density cards with 32 and 64, you can see that it's got this pin out here. Quite often what that does is that plugs into the front of this. And it has a cord that goes to like a terminal strip. And that terminal strip goes right to a location where you can easily land wires to it and get all those wires terminated. Discrete I/O modules. So here we are looking at some discrete I/O. They're showing some different signals here and whatnot, some inputs and some outputs kind of thing for field devices. Some of the different voltages here you can deal with 12. Most everything you're going to deal with in industry is going to be 24 volts DC. In the last 10 years or so, they've really pulled away from the 110, 120 volts, and now they're really focusing on the 24 volt DC, just because of the possibility of getting shorted and shorted to ground and causing people to get hurt. So they stick with the 24 volt DC in most everything. All the cards receive their power from the power supply. So as you can see here on the left, that power supply feeds all the cards using this backplane. That's pretty typical even with all the new equipment. The one thing that is different in the newer equipment is that you can put the power supply in more than one slot. So it doesn't necessarily have to sit to the left anymore. It can sit anywhere on this bus bar, and you can have more than one power supply if you need more power. The discrete input, the basic module block diagram, just a little bit on the heavy side, but anyways, they got the input signal coming into the card. They do some fancy stuff with some rectifiers and a diode, and then the opto isolate. This is a good point to share, is the opto isolation. What that means is that it separates any transient currents or leakage current or voltages or anything that you could possibly apply to it here will not get to this point. It basically is optically isolated. What that means is that when you see power here, it turns on an LED. That LED transfers light to a transistor, an LED style transistor, and that's when it sees that light come on, it closes this contact on this side, allowing the contact in the processor to turn on, to turn that bit on. Essentially is how it works. Here's more of a wiring diagram. This is exactly it. The diode turns on the transistor, and then the digital logic circuit turns on. Again, same thing with the outputs. We got here we got the processor turning on some logic circuits. That turns on the LED. The LED turns on the transistor. The transistor turns on this electronic switch, whether it be a relay, whether it be a triac, or there's several different combinations that they use, transistors, whatnot, and that turns on the output. And here's an illustration of that. Here they actually have a triac switch for that, and as you can see, they do fuse this particular one. Some of them are fused each individually, some are not, so you just need to be aware of that. Okay, individual AC outputs are usually limited by size of triac of 1 amp or 2 amp. It's been my experience that most of the time, if you get if you're looking for power out of your outputs, usually do the relay output, which gives you the 2 amps. Not too many people are using the triac, and all your outputs are 24 volt DC now, so AC doesn't really apply much anymore. Here are the 3 different styles that you typically will see. The coil relay output, which is probably the most common. The triac, which is not used too much anymore for AC because no one's using AC too much anymore, but if you are, that may be a possibility. And then the transistor. The challenge with the transistor, of course, that it is always low voltage. It's going to be something in the 5 volt range. Syncing and sourcing. As you can see, one of the points that all they're doing is they're flip-flopping the positive and negative. See how the common over here is tied to negative here? This is called the syncing module. And when the positive is tied to the positive side of the common, that's called a sourcing module. The key to this is you got to make sure when you have a syncing module, you use what? A PNP sensor. When you have a sourcing module, you have to use an NPN sensor. Easy way to keep this in mind is if you're positive going to the device, you need P as in positive in. So PNP, so positive in. N being it's got its own negative, or usually there's a negative wire to it, and then P going to the 1. That's how they call it PNP. NPN will be negative going into it, positive ground, or negative going out of it. So that's the way to think of that. So that's how I keep that in mind. And the same thing with the output. So if you got a sourcing module, that means that you have positive being fed to the common, and you have positive coming out of each one of these. When you close that contact, you got positive power here. When you supply negative voltage here, when that output turns on, it supplies a negative voltage here. Most, again, your wiring in this case is going to be a sourcing output, and your inputs are always going to be syncing. So keep that in mind. That's the most common anyways. There's a couple of manufacturers that do have sourcing inputs where you have to have a negative power to them, and the only one that I can think of offhand is the Motoman robots. Analog, I want to skip this section just simply because we have, we'll be covering that in later sections. So I'm going to just kind of pop through this pretty quick. Gives you some kind of a little bit of run through on it. Nothing too major here. But I don't want to get too much in depth here because we have one section on that. Special I/O modules, something to just be aware of. The high-speed counter card. One of the challenges we have in the PLC world is that there will be signals that turn on and off faster than the PLC can read. What that means is when you have a system such like a high-speed bottle line, you see these bottles going by it really fast, and that input will come on and go back off again faster than the PLC can read that input. So what happens is, as that signal is going on and off, the PLC is only capturing a certain percentage of those ons and offs. So the information being fed to the PLC is not accurate. To solve that problem, what they've done is they've created a high-speed counter input card. We call it an HSC, or high-speed counter card. And what that does for us is that it captures every on and off signal, stores it locally in that card, the number of times it's gone on and off, and then when the PLC gets a chance to read that card, it goes out and says where you're at now. How many counts do you have now? How many counts do you have now? Every time it goes out and scans that card, how many counts do you have? So it's just coming out and dumping that information right to the PLC. So the PLC comes back with, I'm at 10 counts, I'm at 20 counts, I'm at 30 counts, I'm at 40 counts. Every time it goes out and reads it, as it's continuously counting, it's capturing every count, not missing a beat. It works pretty darn good. Thumb wheel module, nothing you're going to run into too much these days, but basically you can enter a value on this thumb wheel, and it dumps a value in a BCD format to the PLC. And we'll be talking about numbering systems soon. High-speed counter card, again, typically ties right to an encoder. That way it can read all those counts from the encoder, and we'll be talking about that soon as well. Basic or ASCII2 modules, you don't see those too much anymore. Everybody's using Ethernet now, so I'm not going to discuss those too much. A stepper motor module, that's a definite possibility you may run into. It's much like a servo system, only it uses a little different technology. But they do make modules that will talk directly to a stepper module. BCD output, again, I think we'll be talking about next section. We'll be talking about BCD numerics, but at this moment I'm going to just stick with the. This is a type of display that's going to give them provide numeric values to the operator that the PLC has come up with. PID modules, they make them for the PLCs. This is how this is like a process control type thing, where you're, like in this example they're showing here, where we're trying to maintain a value of a level of water in a tank. Proportional, integral, and derivative modules is what it's called. A lot of that's done right inside the PLC now. You don't need external modules like this, but they'll have an actual card that goes right into the PLC that takes care of all this information for us. So. Those are rather in depth, and we only just touch on them here in this class. Motion and position, again, servo controllers. Again, that's kind of a high-end card with a lot of information going in and out of it. But it is just my position here to just let you know that they make input, or they make a card that slides into your PLC that will control a servo system. Serial communications, again, you're not going to see too much of this anymore. Most everything's gone to Ethernet. I can't imagine why anybody would be building a new system using serial. If you may run into some older systems with serial, it's slow, cumbersome, and the configuration is to get that stuff talking is usually very troublesome, especially now with all the latest technology. They don't support a lot of the data communications through the serial ports anymore. Okay, I/O specifications. So they're talking about a little bit of the nominal input voltages and whatnot. They got AC or DC. You're only going to be dealing with 24-volt DC. I'm very confident of that. Only in special applications, maybe some really old applications, you'll see something like a 110-volt input. When I first got into this business, there was such a thing as a 480-volt input, believe it or not. But everybody's kind of stepped away from that, and you're going to see something in the range of 24 volts for pretty much everything, inputs and outputs. The same thing with the output. You're going to see 24 volts DC. They're talking about some really low currents. You're looking at some very small currents for operation, so it doesn't take much current to turn on an input, nor does it take much current to turn on an output. So talked about a little bit about optic isolation. Let's see here. Backplane. Just have to be aware. This is a configuration thing. Something that I don't see you guys getting involved in right away. But if you do get into PLC design, layout, that kind of thing, PLC power supply is kind of critical when you're designing a racked or a modular system. You need to know how many cards are going to go in your rack, and how much power each one requires to size the power supply properly. I know a lot of people, they just grab the biggest power supply available, that way there's never an issue, which isn't bad practice, because it's usually a good practice to oversize, just simply because as industry continues to be updated and things continue to progress, usually there's some sort of progression of improvement in the system, and more power is always required, it seems. So it's not a bad practice. Skip the analog a little bit here. CPU. Okay, so we're talking about central processing units. Here we've got a slide-in or a modular style that slides in the front of it, and then on the left we've got the shoebox, or the fixed I/O unit, which has a defined processor. So CPU, of course, executes the program, stores everything, all the memory locations, all that information. Communication interface, as you can see here in this application, it actually has 2 Ethernet ports in it. Also, you got a USB port in it. It's got all this LEDs and everything pretty much associated with controlling the system is in the CPU. The power supply again, as we mentioned before, is typically on the left, but not always, not anymore with all the latest technology. But it does supply power to all the backplane. Kind of cover that. Here's a good picture of a processor. This particular one actually has a serial port on the face of it and an Ethernet port. Typically, you're only going to see the Ethernet ports on the CPU anymore. It does have a key that switches from run, remote run, and program mode. This is something we'll be getting more and more in depth with in the future, but in run mode is the only mode that the PLC will actually run, will just run the program. In remote mode, the PLC can run the program and be remotely programmed. And in program mode, the PLC can only be programmed. You can't run your program in program mode. So just a couple of points there that I wanted to share. Memory design, again, I think I talked about this a little bit in the last section. You won't even find a 1K processor, I don't think, anymore. I think the smallest you'll find would be a 32 meg, but there might be a 16 meg out there, but I don't think you're going to find a 64K either. Everybody's gotten away from that smaller stuff and really moved into the 32-bit technology with the larger memory. So memory location information, that's good to know. When you're dealing with words, typically a word's going to be 16 bits. The new technology requires a 32-bit word, so be aware of that. There's a definite variation there. But a byte is still 8 bits, and a bit is still 1 bit. So even with a 32-bit word, there's still 8-bit bytes. The processor memory input image table. I mentioned a little bit of that before, where I'm talking about data tables. The processor, the CPU, the whole PLC process does nothing more than manipulate data tables. That's all it does. So when you think PLCs, I want you to think data tables. And what a data table essentially is it takes information like in this illustration here from an input module and places it all in nice neat rows and columns for us to view on a data table. The PLC, when you're writing your program and whatnot, all you're doing is addressing these locations to determine whether a bit is on or off, or you're going to turn a bit on or off, or maybe a whole series of bits that equate to a word of information. But we'll be getting more and more into that in the future. So here we are looking at an illustration of data table and inputs versus outputs. So as you can see here, when he makes this input, you'll see that switch from a 1 to a 0 here on the data table. This data table is being updated from this I/O card. So this information is being extracted from here and dumped to this location. It is our job as a programmer to know what location we're looking for, put that address here to extract the information from this location to here to turn on this output. So here we are kind of illustrating the same thing in the output world. So here if we're at a 0, we're off. If we're at a 1, we're on. And this is the output data table. Noting all those outputs turn on and off. And we see the lights turn on and off here in the I/O simulator. Memory types. So we got non-volatile, volatile, and all this business. So what does all that mean? Okay, so non-volatile means the information will be stored or recoverable through like a loss of power. Volatile means we're going to lose that information if we lose power. You know, probably some of you guys have experienced some of this with your laptops maybe, or personal computers where you lost your battery, you lost some information because you lost power and your battery was dead or something of that nature. Kind of the same idea. Most of our modern PLCs have a flash memory now. So before they lose power, they flash all the memory and store it on the PLC, so that information is stored before it loses power. So it's the new modern technology there for that. Read-only memory, of course, our ROM stores and cannot be changed after the chip has been manufactured. So that's another style of memory chip. Random access memory, or RAM, is often a temporary storage, and I don't think you get too much involved with this stuff anymore with most modern PLCs. Most everything that we're dealing with is in the RAM, but it's stored as flash RAM. They call it flash RAM. And then an EEPROM. This is something that we dealt with when I was in college. I know they're still out there, but erasable programmable read-only memory. You have to expose a window to the UV light, and then it erases it. And that's using special equipment to erase it. So it's nothing that you guys will be seeing, I don't think. The same with electrical erasable EEPROM. I doubt you'll be dealing with any of this stuff. Maybe, but I doubt it. So I'm going to buzz through some of that. Human-machine interface, HMIs. We talked about those a little bit last section. Again, here's some more illustrations of them, how they're used, how they're interfaced. They are really handy. They have their own database, so they talk directly to the PLCs. They write to the data table just like the input and output cards. It's really handy, so you can set up inputs and outputs inside here. You can set up words and information to read or write to the PLC with. It's pretty handy. And then here's some more different aspects of it.